Electrons move around the nucleus of an atom in concentric orbits. These orbits or shells represent different energy states that electrons can exhibit. The farther an electron is from the nucleus, the greater its potential energy. While electrons typically remain in their prescribed orbital energy level, it's possible for an electron to be knocked from its lower orbit into a higher one. Thus, a bombarding free electron can collide with a bound electron, raising it to a higher orbit or energy level. This electron is now in a state of excitation. However, this higher orbital status is fleeting. The electron will be quickly drawn back toward the nucleus and return to its original orbit. During this transition back to its normal state, a single photon of visible light is emitted. This repeating sequence of electron excitation followed by de-excitation is the basis for the functional capacity of a fluorescent light bulb. A typical fluorescent bulb is filled with argon gas and a minuscule amount of vaporized mercury. The inner surface of the tube is coated with the powdery phosphor substance. At each end of the tube is an electrode with filaments. When heated to a high temperature, they emit or boil off electrons. An AC voltage pulse supplied by a starter pushes the electrons from one end of the tube to the other. If one of the free electrons collides with an electron of the mercury vapor, the electron is bumped from a lower to a higher energy level. The electron quickly returns to its lower energy state and in the process releases an ultraviolet photon. This photon is then absorbed by the electrons of the phosphor powder lining the tube, again exciting electrons in the process. This excitation is followed in turn by de-excitation and the release of a low-frequency photon. The photons from all these reactions combine to produce the glow of white light, characteristic of fluorescent bulbs.